see the packing efficiency for the face-centered cubic arrangement, where the constituent particles will be present at the center of the faces of the unit cell along with the 8 corners, right? Now just here we have got this cubic unit cell and I have just taken only one face here, where I have shown the constant particle present at the center of the face. And here let me tell you that AC is the phase diagonal and AB is the edge length, which is denoted by small a. Now let us first find out that how many atoms per unit cell will be present in FCC arrangement. So it is 1 upon 8 into 8 plus half into 6. In our last classes we have discussed that why we are getting its half 1 upon 8 into 8 and this is half into 6. Now the contribution of each corner toward this particular unit cell is only 1/8. So it is getting multiplied by the number of the corners into 8. Similarly, why we are getting half? Because the constant particle or the atom which is present at the center of the face is the part of the 2 unit cell. So its contribution will be to the 2 unit cell. So for this unit cell it is only half into 6. So we will just get added 1 plus 3 will get 4 atoms. So students, so we have got 4 atoms here. Now we are assuming the atoms to be in a rigid sphere. So the volume of 4 spheres in the unit cell will be 4 into 4/3 pi r cube. That is volume of one sphere. Right? So it's a 416 upon 3 pi r cube. I've just done it by the equation 1. Now next is the volume of unit cell. So here the unit cell is in the cubic form. The cubic unit cell. Right. So for it we will use the formula A cube and for it we require A, that is the edge length. So we are going to find it out. So in here in triangle ABC, the AC square, which is the face diagonal, is equal to AB square plus BC square. We are applying the Pythagoras theorem here. So from here we will just find out that AC is equal to root 2A. Now just see this figure here, this diagram here. So I have shown these 4 spheres which are just close to one another. They are present at the corners, right? Now this one is the atom or the sphere which is present at the center of the face. You can see here that the 3 spheres and along the AC, that is face diagonal, are touching one another, right? Or you can consider this one also, but since here in the diagram we have taken AC, so this is there. Now A, this is one atom, its radius is R. This is the second atom which is present at the center of the face. So here it is 2R, its complete diameter will be taken, and the third sphere at the C point is this one, it's again R will be taken. So it's R plus 2R plus R, it will come finally 4R. So AC value comes to be 4R here. Now we'll just put the value of, instead of AC we will place here 4R, it will become root 2A. 4R equals to root 2A. So A will be equal to 4R upon root 2. Just rationalize it and then into root 2 upon root 2. So AC equals to 4R root 2 upon 2. Just by cancelling we'll get 2R root 2. So the edge length A of the unit cell is shown by 2R root 2. Now next we'll just find out the volume of unit cell. It is A cube. So it is 2R, A we have just calculated here, it is 2R root 2. So 2R root 2 whole cube. So we write here 2 cube, this is R cube, this is root 2 cube. So finally it will become 8 into, from here root 2 into root 2 into root 2 will become 2 root 2. This is 2 here, R cube, and this is the root 2 here. So 8 to 16 root 2 R cube. So we are getting the volume of unit cell, it is 16 root 2 R cube. Now just come to the formula packing efficiency. So it will be the volume of 4 spheres upon volume of unit cell into 100 to make it into percentage. We will just put the value of the 4 sphere. It is 16 upon 3 pi r cube upon volume of unit cell 16 root 2 r cube. So here the r cube and r cube will get cancelled. 16 with 16. So we will get pi upon 3 into 100 upon root 2. So you can put either the value 22 upon 7 or you just put the value of pi 3.142 into 100 upon 3 into root 2. Its value is 1.414, and just by cancelling it you will get the value 74%. So students, 74% is the packing efficiency of face centered cubic arrangement, which is the maximum packing efficiency. Students, now just next we are going to do the packing efficiency of body centered cubic arrangement, where the constituent particles are arranged along with the 8 corners at the center of the body of the unit cell. Now here in the body centered cubic unit cell arrangement, the cubic unit cell will be of the type BCC, where the number of the atoms per unit cell will be 1/8 into 8 plus 1. So here this is the contribution of the atoms present at the 8 corners, and this is the contribution of that atom which is present at the center of the unit cell, which is not being shared with any other unit cell in its surrounding. So here we will get 1 plus 1 equals to 2. So how many atoms are there in BCC unit cell? It is 2. So we are going to find out the volume of the 2 atoms in this type of unit cell. So it is 2 into 4/3 pi r cube. So we will get 8 upon 3 pi r cube. So volume of the atoms which will be present in this unit cell is 8/3 pi r cube. Now we have to find out the volume of the unit cell. And to find out the volume of unit cell, we have to first find out the value of A in terms of R. So in the previous topic, we have just calculated out AC. So what was AC here? It was root 2 A. Right? So in triangle ABC, we will just find out this hypotenuse length is A and this is A. So we will apply the formula Pythagoras theorem and we will get that AC square equals to AB square plus BC square. So just putting the value of A, and A will get the value of AC, that is root 2 A. Now we have to find out the AD here. Right? So AD is the body diagonal here. Now the AD square is equal to, we will consider triangle AC and D. Here we will find out AD. So AD square equal to AC square plus CD square. So just putting the value of AC, we got root 2A here, root 2A whole square plus A square. So AD square equals to 2A square plus A square. It will become 3A square. So AD will be under root 3A square. So finally we are getting A root 3. Now AD. Now AD is the body diagonal. Right? And the 3 atoms are placed along this body diagonal. So if they have been considered to be spared, then we will just find out the length of the AD in terms of R. So it is R plus 2R plus R. So AD is equal to R plus 2R plus R. So it will become 4R here. So we get AD equals to 4R. Right. So 4R equals to, this is AD value A root 3. So 4R equals to A root 3. So what will be A here? It will become 4R upon root 3. So once we get the edge length in term of R, we are going to write down, find out the volume of unit cell. So we know that the volume of unit cell is A cube. So what is the value of A? We got it from here, 4R root 3. So we have kept here, so it is 4R upon root 3 into cube, upon cube, whole cube, sorry. So it will become 64R cube, root 3 into root 3 into root 3. So we'll get 64R cube upon 3 root 3. This is second equation. Now we are going to find out the packing efficiency. So the packing efficiency will be equal to the volume of the two sphere upon the volume of the unit cell multiplied by 100. Just put the value of the volume of two sphere. This is there 8 upon 3 pi r cube upon volume of unit cell is 64 r cube upon 3 root 3 into 100. We are just going to cancel it out and we get pi upon 8 into root 3 into 100. Put the value of pi 22.7 or 3.142 into root 3 value 1.732 into 100 upon 8. Just by solving this, you will get 68%. So this is the volume occupied in BCC. It is 68%. Right. Now, in just nutshell, to cover up the packing efficiency, when the arrangement of the crystal have the simple unit cell or simple unit cell arrangement, then the packing efficiency comes to be 52.4%. And when it is face centered cubic arrangement, right, it came how much? 72%. Then the next is the volume occupied in the BCC arrangement, 68%. So you will find that the best packing efficiency is the face centered where the maximum space is being occupied.